In today's video, we're gonna discuss pharmacokinetics of oral drug absorption through one compartment model which obeys first order input and first order output that basically employs over immediate release dosage forms which directly goes into the gastric pH or through gastrointestinal tract or oral route and get absorbed and afterwards eliminated with a certain rate. Since it's an oral one compartment model, it consists of two types of rate constant, that is Ka and K. Ka is an additional rate constant that is present in oral one compartment model, not present in IV bolus or parenteral compartment models. Since its bioavailability is 100%, so we didn't consider in its rate. But as far as this oral route concerned, the rate of absorption does matters because bioavailability isn't 100% or isn't cent percent. So we need to find this rate of absorption over here with the rate of elimination. So which you will get a proper concept regarding one compartment model, oral one compartment model, that is present on Sharjil page number 202, question number 1. Let me read it for you. Plasma sample from the patients were collected after an oral bolus dose of 10 mg of a new benzodiazepine solution as follows. It is the data that is given, that is taken from plasma samples. So at different time intervals and their concentration that is present in this plasma, in the patient's plasma actually. And from this given data, we need to find the elimination rate constant, that is K, the Ka by feathering method. Feathering method is the main objective on which I'm going to make this whole video. And with the determine the equation that describes the plasma drug concentration of a new benzodiazepine. Okay. So for that, first we need to form the data for this question. The table is given here, so I'm not copying it. While we have to write the dose, that is 10 mg taken by the patient. And afterwards we are getting the concentration from its plasma level with different time interval. Here we have to plot a graph on a semi-log graph paper, and between the concentration and time. Concentration on the y-axis and time on the x-axis. Here the unit of concentration we have is the nanogram per milliliter and the time is given in hours. Right. So we're gonna plot it by increasing dots. This is the graph we got after plotting. And the targets which we need to find is the elimination constant, that is K, we need to find, and the absorptive constant, absorption rate constant. That is being denoted with Ka. For that, we are using graph for both of these. This is our first task, this is the second task. For the K, as we had used in the one compartment model, an IV bolus, that is K is equivalent to first order reaction. K is equivalent to minus slope, and slope is equivalent to ln C2 minus ln C1 over T2 minus. So we can get the C1 and T1 and C2, T2 by extrapolating it. For the extrapolating, for the constant, elimination constant K, we are going to extrapolate from this line. Okay? We'll take or we'll decide 2 points from this line. Exclamation. I'm just extrapolating this straight line towards y-axis so that I can find the initial concentration. Okay, let me highlight it with another color. That is blue. Okay, so you can easily differentiate. Okay, so this is the extrapolation we did, and from this we can get this, that is almost 4.75. Yeah, so another point I'm taking here, since, just focus on it. See, the line is at just the junction of this box. So I have decided this one to take so that I can get an accurate reading. Elimination rate constant, not the absorptive rate constant. This is the state of it. The data we get by extrapolation, that is C1 equivalent to 17, while the T1 is equivalent to 11.5, C2 is an equivalent to 10, while the T2 is an equivalent to 17.5 on. Okay, so let me put its value. C2. Now I have put its value. We can easily calculate it in the calculator. Upon ln 10 minus ln 17 over 17.5 minus 11.5, and it's minus 0.088. That is minus slope. So the minus sign from here would be nullified. And slope is an equivalent to, which we already know, equivalent to K. That is the rate constant, elimination rate constant for the first order context. Now the QD, the main target, that is absorptive rate constant. For this, we are going to use these starting points. These starting points, are they visible? Yeah, yes. Okay. You already know that we have extrapolated it from this line. So what we are going to do is to extrapolate these lines towards this. Right? Wait, I have extrapolated 3 points. It is up to me that I can either choose these points or I can extrapolate with any other. But it must be more than 2 because you are going to find the residual concentration. By this extrapolation towards this extrapolated line, we can get C3 from this C3 point, we can get C3 bar, from C2 we can get C2 bar, and C1 we can get C1 bar. From the absorptive rate constant, you need to extrapolate in this manner, which I have already shown you. Like from this side of your curve, you have to extrapolate or decide any 3 or more, it should be more than 2 points, so you can extrapolate it over this extrapolated line that we had done while doing the C1 concentration, which is 5.4, and the extrapolated value of this C1 is C1 bar, that is equivalent to 45. The very next point is C2, that is here. Okay, you look. C2, that is 10, 11, 12, C2, 12, and the extrapolated line of this C2 is C2 bar, that coincides at 42. Alright, that is the last point we get is C3, and the concentration over here is 19. Sorry, it's 18. Since it's 19, sorry. Look at this. This is the point, and the one small box is equivalent to 1 unit between this cycle that is between 10 to 20, and the C3 bar is 36, definitely. From these concentrations, you're going to find residual concentration. That's actually the main target, which is being denoted by CR1, CR2, CR3. It could be more than 3. It's up to you, but it should be more than 2. So, for determining these CRs, you can C1 bar minus C1, C2 1 bar. In this manner. And what you're gonna get is 45 minus 5.4, 42 minus 12, and 36 minus 19. Calculate the respective concentrations. 30, 36 minus 9 to 17. these three concentrations, these residual concentration, you're gonna plot these concentration on the same time, but the concentration varies, okay? On this graph, unfocus it, this graph, you're gonna plot these three concentrations. I'm going to plot same time, that is 1.5. I have to plot on 39.6. That is 39.6. Over here. I got this. And again, 30. And then 17. 20, 19, 18, 17. So, join it. That is the line we get. Afterwards, what you are gonna do is to extrapolate from this line and follow the slope procedure. Okay? With the help of extrapolation, I am going to choose this point for extrapolation. That is for the Ka. The one point I want to choose is this. The concentration is 20. See, the concentration is 20. The point over here. And this will lie on. Wait. Now, the concentration is 20 and it is falling on 2.5 with the time 2.5. Let me extrapolate it as well. And the very next line I want to choose is this one, since you can focus it. You can see it. I think you can. Okay, because it is at the junction, so I can take its reading easily. You may take, it's up to your will, so you can take anyone you want. Okay, I'm just extrapolating it in order to find the slope of Ka. That is from here. See, I'm going to write this. That is T2 here, C2, and the C1 right over here, T1. It's 2, C1 and T1 is, C1 is 32, 32, while the time taken by C2 is 1, okay? Is it visible? See, the extrapolation over here. The T1 is 1 and T2 is in between 2 and 3, so it's 2.5. Okay. From this step, you can determine, since K is an equivalent to minus slope, for first order reactions, C2 minus C1, ln C2 minus C1, T2 minus T1 for the data. I have put the values and now calculating the slope. That is minus 0.2921. That is minus slope. You can cancel these minus. It's Ka equivalent to slope, and that is 2.2929 per hour. It is already second target has been completed. The part C, which tells us to prescribe or describe the plasma drug concentration for a new benzodiazepine, describe an equation. The equation we are gonna use, the equation which oral one compartment model follows, is Cp is equivalent to Cp naught. Cp stands for plasma drug concentration. The concentration or the amount per volume in plasma is denoted by Cp, and naught is the shows the initial plasma concentration. Right? It is bracket e to the power minus Kt minus Kat. We don't know the Cp, but we do know the initial concentration that we had found previously 4.75 nanogram per milliliter, 4.75 nanogram per milliliter, and then E minus K. The K elimination rate constant we had found, that is 0.088. 0.088 T, since we don't know T, E minus Ka. Ka is 0.2921 T. So this is the equation that best describes the plasma concentration of new drug benzodiazepine. Here is the end of this schematic.